In this video, the learner will identify vector quantities and make a sketch of a vector. We're going to talk about the difference between two terms first. The first term is vector, which is a quantity with both size and direction. So it will have both a value and a direction specified. A scalar is a quantity with only size. So when we talk about both of these terms and we say that word size, we're really going to start using the word magnitude. So whenever I use the word magnitude, I'm really talking about the size of that quantity. So for example, if I have a box and I decide that that box needs to be moved, and I'm going to move it 8 feet. 8 feet is the size or the magnitude of the movement. That 8 feet is the distance between my initial point here and the ending point where I stopped moving the box. So it didn't matter which direction we moved it, that's why we only say that that was distance. But if I then talk about the 8 feet being the magnitude, and then say I moved it 8 feet to the right, I'm then talking about a vector quantity because I've implied magnitude and direction. This is what we call displacement. So it's how far or the size or magnitude of the quantity and the direction. Now we're going to take a look at some quantities and decide whether they're represented by a vector or a scalar quantity. The number 7 is a value that only has a magnitude. The number 7 is only a size. It does not have any direction. So this is only going to be a scalar quantity. The angle measure 15 degrees. So if I were to draw that angle, say on this XY axis, I could draw 15 degrees coming from the horizontal. That implies direction. So I know the direction that I'm going, 15 degrees from the horizontal, but I don't know how far I'm going 15 degrees in the horizontal. So I don't know where my vector needs to stop. This arrow implies that that's going to keep going. Therefore, this quantity has direction but no magnitude. So therefore, this is just a scalar quantity. The segment between 0, 0 and -2, 6. Well, if I take a look at graphing that, -2, 6 is the point here, and I have the segment between 0, 0 and that point -2, 6. This has both a direction from 0, 0 to -2, 6 and a size from 0, 0 to -2, 6. We could find that size by doing Pythagorean theorem and finding the length of that segment. So with both a magnitude and direction, this could be represented by a vector. Taking a look at the sum of +7 and -3, which is +4, we follow the same argument as we did for the number 7. +4 only has a magnitude, not a direction. Therefore, that will not be represented by a vector. We have a couple more examples here. Which of the following can represent a vector? The first example states the length of the distance between the points 0, 0 and 2, 7. This just talks about a quantity between those 2 points. It doesn't tell us what direction we're going in, whether we're starting at 0, 0 or whether we're starting at 2, 7. So because we don't know that what direction we're going, this cannot be represented by a vector. The line segment beginning at +2, 7 and ending at 0, 0. Well, we know we're looking at the segment between these 2 points, so we could find the magnitude of that segment, either by distance formula or Pythagorean theorem on the coordinate plane. And we know the direction starting at 2, 7 and ending at 0, 0. So therefore, this is a vector. The length of the distance between the points 2, 7, and 0, 0. This follows the same argument as the first one. This describes the magnitude of the segment between those 2 points, but it doesn't tell us the direction, so that's not a vector. A line segment beginning at 0, 0 and ending at positive 2, 7. We're talking about the length between 0, 0 and 2, 7, which implies magnitude. But we also know where we're starting and where we're ending. Therefore, we know the direction that we're going. So this could be represented by a vector. Problem 2. Which of the following can be modeled by a vector? The length of the distance between the white ball and the black ball on a pool table. This follows the same argument as our line segment. We're talking about the length between those two, but it doesn't tell us if we're starting at the white ball or the black ball. So we don't know a direction. We would only know the magnitude. Therefore, that cannot be a vector. An order in a restaurant where 4 people ordered 2 items each. This is only talking about an amount or a magnitude of a quantity. Therefore, we do not have a vector. The length of the distance between a table at a restaurant and the kitchen. Again, talking about magnitude, but not talking about direction. The movement of an airplane. The movement of an airplane does follow direction, and we would follow the flight path, which means we would know how far away that airplane is. Therefore, we could use the movement of an airplane to model vectors. Now let's talk about what a vector looks like and how to name it. So here is vector A or vector AB. We would name it with our initial point or our tail as our starting point, and our terminal point or our ending point or tip is going to be the last point that we use. So we would name this vector AB, or with that lowercase letter here, vector A. Now we're going to talk about how to sketch a vector. Remember, the magnitude is the length of a vector from its initial point to its terminal point. So it'll be the length between those 2 points. The direction of a vector can be expressed as an angle, either with the horizontal or using cardinal directions, north, south, east, and west. As an example, we have vector AB. The direction of A is 30 degrees relative to the horizontal. So we have the vector A, which has a magnitude, and the direction of 30 degrees. Or we could look at a vector AB, where the direction is 60 degrees east of north. So starting at north, we go 60 degrees to the east, and that's the direction of our vector. Okay, so we're going to try and sketch a couple. Vector M, which is 15 miles per hour at 140 degrees to the horizontal. 15 miles per hour is our magnitude. That tells us how much of that vector we have. The 140 degrees to the horizontal is our direction. So from the horizontal, we're drawing 140 degrees, and we'll go ahead and label our magnitude of 15 miles per hour. Another example, we have vector C with 55 pounds of force, 55 degrees west of south. Well, we know we're going to start west of south, so south will be where we start from, and we're going to draw 55 degrees in the western direction from south. So south is here, open up that 55 degrees, and there is vector C with 55 pounds of force. Next, we're going to talk about another way to sketch vectors. We're going to talk about navigational bearings or headings. This has a lot of application in boating or aeronautics. So this is how you'll hear airplane directions or vectors being written. So when we have a single angle given, it is understood that the bearing is always measured in a clockwise direction from due north. The bearing from A to C is 30 degrees. So we have an example here. A bearing from A to C is 30 degrees. So starting from north, going in a clockwise direction, we have vector AC. Another way to write this, or to hear this, is starting with a north or south line and then uses an acute angle to show the direction. So the bearing from A to C is south 52 degrees east. What that means is 52 degrees east of south. So starting at south, we're going to move 52 degrees east. So from south, move 52 degrees to the east, and we have vector AC. I put our cardinal directions on here as we look at these examples. We're going to give a diagram to represent each of the following. A bearing of 210 degrees. Bearings, giving that single angle, means we're going to start from north and go in the clockwise direction, 210 degrees. Well, 210 degrees from north is, well, 180 would be completely down here, and then 30 more, we would end up at this light blue vector here. So that would be a bearing of 210 degrees. It's worth noting that the concept of navigational bearing is different from the vector direction in physics and geometry. When dealing with those in class, in geometry and physics, direction always starts from the positive x-axis. When talking about navigational bearing, it's starting from true north. So you need to keep that difference in mind as you look at navigational bearings versus examples in geometry and physics. In geometry and physics, you'll still see examples like this, north 42 degrees east, which means starting at north, we're going to go 42 degrees to the east. So starting at north, go 42 degrees to the east, and we'll end up at this blue vector here. South, 72 degrees west, means starting at south, move 72 degrees to the west. So south is, of course, down here. Starting at south, move 70 degrees to the west, and we end at this vector here at 72 degrees.